Greetings and welcome, friends. Mr. Wada here. Today we are talking about, properties of parallelograms. I just had my friends in real life, my math buddies, do some Geogebra Sketch work with parallelograms. We discovered, or we recognized some trends, some patterns. We're going to prove some of these properties today, and the rest you guys are going to discover in your homework or prove in your homework. So let's take a look at this. So a parallelogram, that would be a good thing to know, is a quadrilateral. What's a quadrilateral? Quad, that sounds like four. Yeah, it's a four-sided polygon. Okay, so a parallelogram is a quadrilateral with both pairs of opposite sides parallel. It would be pretty difficult for adjacent sides to be parallel. No, that just isn't going to happen. All right, so here's a parallelogram by definition. So based off of that as my given information, right, with opposite sides parallel, notice that the double triangles indicate that these are parallel to each other, but not to the other original set. Using this as my only starting information, and then doing things like, making a triangle or something, I can use all of my triangle theorems, I can use all of my parallel lines cut by a transversal theorems, and I can prove a whole bunch of new properties about these parallelograms. So here we go. So here's a couple theorems coming at your face. Theorem 7.3, parallelogram opposite sides theorem. Post. I've never called this post, but it is. If a quadrilateral is a parallelogram, done. All right, so imagine we knew that these were parallels. Yes. Then the opposite sides are congruent. Wonderful. Wow. There you go. All right, so opposite sides are congruent. You guys saw that when you created your sketches. Sketches, right, Jack? So let's see. And then it also turns out that opposite angles are congruent. We have done some proofs back in the day with two sets of parallel lines where they were one another's transversals, Alyssa. And you might remember that we were able to kind of prove these situations. We didn't have a name for these types of angles because they weren't with respect to one another's parallel lines or transversals. But within a parallelogram, notice that the opposite angles are okay. Good times, good times. Let's do a proof. Do a proper proof here. All right, so get yourselves ready for this. And oh man, I love these proofs. Go. All right, given this is a parallelogram, so let's write my gimmies. Gimme. All right, so it's a parallelogram. Prove that the opposite sides are what? All right, let's see what we can do here. So I think, let's see, we can draw a diagonal as such, and either diagonal would have worked. And notice that it conveniently constructs two triangles for me. So I've got the given there. I think I also have some alternate interior angles going on. Does anyone see any alternate I could work? Let's see. Or should I deal with consecutive? PQS. Oh, they're dealing with this guy's the transversal. I was looking at these as the transversals set. Aha. So okay, so PQS right here and this guy are congruent. And then the other set are congruent. Makes sense? So let's write that out. So angle PQS is congruent to angle RSQ. And alternate interior angles theorem is the reason. And then I also would have angle RQS is congruent to angle PSQ. For the same reason, right? So I've labeled that as such. Now I'm trying to prove the opposite sides are congruent. I don't have a way to do that right now. What are you thinking, Jack? Oh, okay. So you're saying if I could prove these two triangles are congruent, then maybe I'll be able to show that their corresponding parts are congruent? Okay, so right now for these two triangles, I've got angle and an angle. I need a side somewhere. Evan, what are your thoughts? Oh, we love the reflexive. So QS is congruent to itself. I'll even say SQ because these happen to be like a rotation of each other, but whatever. I would have been fine even if you were the other way. So reflexive property. And now I think I could say that these triangles are congruent. Let's see. Dare I try to name these triangles? So I'll do PQS, I guess. And let's see. So PQS. So then the next one would be R to the S to the Q. Well, I started for P. I started at the one away from the side. You could have named these triangles 6 different ways. So as long as for you, you've lined up the corresponding parts, you're good. Why are these triangles congruent? Angle, side, angle. And now that I know these triangles are congruent, I believe I could say my proven statement, both of them in fact, that PQ is congruent to RS, and that QR is congruent to SP. Why is that? Say, pay, say, tay, say, right? Lovely. Right? Corresponding parts of triangles are congruent. And so now this thing that we suspected because of our interaction with Geogebra Sketchpad, Anthony, I think you would agree that we have now sufficiently proven it that these opposite sides of parallelograms are always going to be congruent. Todo de los tiempo. Think so. So let's see. Let's get a little example. Right, so once I know things are congruent, you guys know the routine. We then give you an algebra problem within a geometry problem, and then you're experts at it. Okay, so here we go. If I wanted to find x, what should I relate this expression to? 12, and how does this relate to 12? It equals 12, and the reason those are equal is because those opposite sides are congruent by parallelogram opposite side, whatever. And then def of Kong, their measures will be equal, right? So I'll get x equals 8. And then how about y? How does y relate over here? Yeah, because these angles, opposite angles, are going to be congruent to each other. And then by def of Kong, y is equal to 65. That's already solved. Bam. Right? So, and then, sometimes they'll try to make things a little bit more creative and look at what we did here. And, it's man, all right, you're trying. Tell you what, we'll do monitoring progress question 2. I don't even know if I gave you guys this one. Did I? Awesome. Take a look at this one. In case our internet friends are wondering, I'm a little bit faster today than normal because we've got a half day here in real life. I don't know. I don't think days are halved on the internet. But here we go. Okay, if I want to solve for x here, what do I do? What could I relate? 2x. This angle is congruent to this, right? J is congruent to L by parallelogram opposite angles theorem. And therefore their measures are equal by def of Kong. Solve that, divide both sides, get x equals 25. And then, hey, opposite sides are congruent, if I could say so myself. So JK is congruent to ML. Therefore, y plus 3 equals 18. Subtract 3 from both sides, y equals 15. Right? So these aren't that bad. I think it's more interesting, kind of that proof that we just did. Let's give you 2 more theorems. Right? All sorts of theorems coming at you today. And actually, maybe I'll even show that. I think I shall. So here we got parallelogram consecutive angles theorem. All right, that's a nice name. And my awesome parallelogram sketch here. All right, I'm just prepping some things on my side screen. It says if a parallelogram is blah, blah, then its consecutive angles are supplementary. Yeah, that makes sense. I think that proof is just jumping out at me. What reason do you think that's going to be true? What's your big hitter when you write that proof? You think? Why would those be supplementary? What's your go-to theorem you're going to use? Well, if these are parallel, those are consecutive interior angles, and by the consecutive interior angles theorem, we would say that those are supplementary. And then by def of supplementary, I'd be able to say that. So yeah, so that one just kind of feels obvious to me. Also, check this out. I don't think we didn't have time for all of you to get this far, but it turns out the diagonals of a parallelogram, first of all, they're not congruent for a parallelogram unless that parallelogram is what shape? What shape? What type of quadrilateral? A square, it would have congruent diagonals, or a rectangle. So a rectangle is the broad category. A square is a subset of the rectangles. Yeah, that the diagonals will be congruent, but it turns out in parallelograms, the diagonals bisect each other. All right, so that one's going to be a little bit more interesting for us. But here, I was pulling this up. Here's a Geogebra sketch that's just got kind of like all the properties of the parallelograms happening. Look at this. Oh, lovely, lovely. You see the diagonals are bisecting each other. Opposite sides are congruent. Opposite angles are congruent. And we even have that the consecutive angles, all right, 30 plus 150, are supplementary. So look at that. Lovely sketch. Really just wonderful. Right? I actually do like this GeoGebra thing. Look at how nice they label those angles. Right? Like that's cool. I wish I could get that happening in Geometry Sketchpad a little bit nicer. I've tried to construct things like that before. What I'd really like is if they could label double arc and triple arc like that. But anyways, so there's that, in case you were wondering. Let's do a proof regarding the diagonals. Diagonals. Oh, you bisect each other. Wow. It is. I'm actually going to submit it to the International League of Math Friends for this year's awards for, like, best math song. Actually, I don't know if you guys know this, but Mr. Kinlock, he sings some songs about math. I'm not even close. Capacity. In this school, best math YouTube channel in the room, 286. Sure. I was actually, this is just something that I shouldn't record and post on the internet as I'm like thinking out loud. But I was thinking, what if I had students guest host lessons on like my YouTube channel sometime? Like I'll have like some of you guys do like a homework problem once in a while, and I'll even like post it on the internet. But I don't know. Like I'd need like a disclaimer where you guys could, you know, allow yourself to be on the internet that way, like minors or whatever, and your identity couldn't get out there. No. I'm telling you, it's true. Like I can't. Yeah, it's true. And I'll even share the proportional amount of YouTube money that I get. Like if your video is the one that goes viral, yeah, I would give you your fair share. Yeah. That would be interesting. Wow, that would be interesting. Well, let's see. Let's take a look at this. Let's see if we can do a proof. So we're gonna try to prove that the diagonals bisect each other. So here's a parallelogram. There are diagonals that I drew. So let's label the regular gimmies. All right, given. All right, things like that. Whatever. All right, so I'm gonna say, yeah, we've got like parallelness is true by definition of parallelogram, or that's, yeah. All right, whatever. Let's see. I also, if I'm gonna work with these, all right, what sort of plan, does anyone have a general plan as how I could even attack this? There's so much stuff that I could just start naming as being true, but how am I gonna show that M is like the midpoint, or that these diagonals bisect each other? Does anyone have a general plan? Huh. So each triangle, I've got big triangles here. I've also got little triangles. Yeah, I think if we work towards these little triangles, let's try to prove these two blue triangles congruent. The bow tie of the parallelogram is what I'm just deciding to call it right now. Josh, you have a thought? Whoa, man, he's already jumping on it. All right, so angle RMS. Ooh, I see that. And QMP. Okay, what about those? Okay, all right, vertical angles theorem. I wasn't even thinking of going there, but that's a great, Yeah, great option. All right, anyone notice something else that's going to help us here? How could I prove just those blue triangles are congruent? Jack? RS. Okay. I'm glad you said that one. Right, these opposite sides of the parallelogram are congruent because of parallelogram opposite sides theorem post. And we're going to accept that as true because it's been one of the other theorems that we already proved. Even though it was just moments ago. All right, so I've got to prove triangles. I need one more thing. What do we got, Evan? Let's see, PQM. All right. And R PQM and RSM. Yeah. I like it. If we were conveniently proving a brand new theorem right now, I wouldn't, like, because you guys are helping me, I wouldn't just be calling it like the Waddy theorem, which is possibly what Pythagoras did when, like, one of his students may have been the one to discover the Pythagorean theorem. I would actually give you shared name credit as well. Like, if this was somehow a completely new theorem we were aware. All right, I'd give you shared credit. Let's see. So I think I have enough information to prove some triangles are congruent. Let's see. We'll call that PQM is congruent to triangle PQM and RSM. Yeah, we actually can use the same angle names, except for now triangle names. Why are those triangles congruent? Angle, angle, side. Now, if we had gone for this angle and this angle, you also could have ended up with an angle side angle approach to proving that, right? Aiden SD. Right. You're with us? All right. I don't want you getting distracted here. Now, because that is true, what else can I say? Oh yeah. All of the CPCs, PCs. All right. Because corresponding parts of congruent triangles are congruent, therefore, let's see. I'm gonna label this with a different color here. So therefore, this is congruent to that, and then also because of CPCTC. Then PM is congruent to the RM, and then that's CPCTC. And then I think I could say like diagonals bisect each other. PR bisects QS, and QS bisects PR by def of angled segment bisector. Yeah, def of segment bisector is what. And I would just say that, yeah, M bisects. Yeah, we're running out of space. I'm sorry. And PR. All right. So I think it's interesting, right, that we were able to put that to put that proof to, demonstrate it, put it to the test. We showed it using, like, a lot of skills that we previously had. And I just want to point out, like, you guys kind of really put that proof together all on your own as a class, right? You guys just discovered that, right? I pointed you in the direction, but really, you guys have the ability. Here, I'll let you finish writing that. Proof. Wow. I think we've come a long way with proofs, friends. We've got such an awesome bag of tricks now, too. Oh, yeah. I don't. No, what it's about. Wow. Wow. I'll have to check that out. Let's see. Example 2. Here's a table light, desk lamp thing. It says, as shown, part of the extending arm. Leak, Josh, right? Friends? Let's see. The part of the extending arm of the desk lamp is a parallelogram. I believe it. The angles of the parallelogram change as it is raised and lowered. Find the measure of angle BCD. BCD. All right, so that's this angle right here. When angle ADC is 110. How do those angles relate? They are supplementary. So I'm expecting that these two add to 180, and therefore measure of angle BCD is equal to what? 70 degrees, right? So the application of these are pretty straightforward. I mean, they spice them up with some algebra once in a while, but I just wanted us to, you know, definitely see some proofs today. Let's see. I think I'm gonna jump down to example 4 for sake of time. All right. I might have even given you guys a better table than mine. It says, find the coordinates of the intersection of the diagonals, LMNO, with vertices as shown. So let's see, I'm just going to make this my y-axis, this my x-axis. It looks as though all of these points are in the quadrant 1. Right, Haley, right? L is at 1, 4. Here, Isaiah, don't distract my friends. 6, 0. There's Enye, and let's see, what else did I need? 7, 4, M. Over 7, up 4. All right. Actually, here's a question. If I gave you 3 points that form a parallelogram, could you have found the other point? Would you have been able to know that this other point had to be there? What's a possible way I could have found that point? Slope. I like that, Anthony. So you're thinking like the slope between what points? So O to L is up 4 over 1. So up 4 over 1, there would have to be another point right there. I agree. Yeah, slope's a great choice because we are expecting these to have the same slope when they're opposite sides because they're parallel and parallel lines have the same slope. Let's see. I'll try to draw real diagonals here. And so if I'm looking for the intersection of these diagonals, what way do you think I could do that? That's what they're asking, right? Yeah, intersection of the diagonals. We might only just be able to make a plan for this. So this is what I'm looking for, right? That point right there. What would I need to do? Actually, I'll even change the color of one of those lines. All right. If I want to find the intersection between 2 lines, guys, how could I do that? Oh, midpoint formula. That is... Oh, wow. Malik, wow. You just saved me so much time. You know what I was going to do, Malik? Let me tell you what I was going to do. And then you got to say what your better solution was. No, I was going to find the equation of the orange line by finding the slope between O and M and then writing it in y equals mx plus b form. I was then going to find the equation of the blue line by finding the slope between L and N, plugging in one of those coordinates, and the slope in like point slope form, converting it to slope intercept form. I was then going to solve the system of the blue line and the orange line simultaneously. But Malik with the save, what were you suggesting, Malik? Just like the midpoint formula. And which theorem are you relying on to show that? You're relying on the fact that these diagonals bisect each other, right? You actually could midpoint formula this in either way. So midpoint formula, in case you guys don't remember, is the average of the x's and the average of the y's. Wow, with the save, Malik. And because of that time saving, I think we're actually going to be able to finish this lesson before the bell rings. Oh, man, Malik saving the day. All right, here we go. So midpoint formula, let's find the midpoint of Mo midpoint. So Mo money, Mo midpoint. So let's see. 7 plus 0 divided by 2 and 4 plus 0 divided by 2. And that's just going to end up being 7 halves, comma 2, right? Or 3.5, which you kind of graphically might have been my estimate. 3.5, comma 2 is the midpoint, right? Wow. I guess I'll call it Mo midpoint. There we go. I like that. I like that a lot. Well done. Wow, so that was way easier than the means that I was going to do it. Okay, I think I've covered everything I need to, and we discovered so much ourselves. I think we all learned something today. Thanks, everybody. Have a great day.